So this is going to be part 2 of section 4.1, and in this section we're going to compare and contrast the idea of relative and absolute extrema. Right? So first off, sometimes we care about the absolute or the global extrema, and sometimes we just need a relative or a local extrema. So packed in there were two phrases. When we talk about extrema, we can talk about two different types. But unfortunately, those two different types have 4 different names. We can talk about absolute extrema, or we can talk about global extrema, and those two mean the same thing. We can also talk about relative or local. Now, me personally, I like the terms global and local because I think they have more context to them. Global would mean everywhere, the entire thing, whereas local just means on a little tiny interval. Okay? Now, because there's lots of different things we could be looking for, you have to be careful to make sure that you're finding what they want you to find. Okay? So, you have to be careful as to which you're looking for. If the function is on a closed interval, then the endpoints can be absolute extrema, so don't ever forget to check those. All right, so here I have a graph for you, a picture. It is the graph of the function f of x equals x cubed minus 3x squared. Right? There is a high point right here, a hill, if you will, at the point 0, 0. And there's a low point over here, a valley, if you will. And that's the language of this textbook, this author. Larson decided to go with hills and valleys. That's not mathematical terminology necessarily, but it's a way to think about things. Okay? But these points right here, while they might be a high point and a low point, these are not absolute extrema. They are only local extrema, or relative extrema. That point 0, 0 is a high point, and it's a relative maximum, but clearly you can see over here on the graph, there are pieces of the graph that are going to be higher. Right? So it isn't the highest point, but it's a high point on a little interval. Same thing with the valley over here. There's lower points of the graph, but for this little tiny piece of the graph, that is considered the lowest, so it is a minimum. Right? So basically what we're looking at here is, if you have a continuous function, a relative maximum is a high point on a small interval of the graph, and a relative minimum is a low point on a small interval of a graph. Okay? Provided that the graph is continuous, then you can talk about this up-down to find a maximum and down-up to find a minimum. Okay? So if your graph is smooth, then you can find that hill or that valley by just looking for a place where the tangent line is horizontal. Because if we were to draw on a tangent line here at the maximum or here at the minimum, that tangent line would have a slope of 0 because the graph smoothly goes up and then turns and goes back down for that maximum, or smoothly goes down and then turns and comes back up for that minimum. Right? So one of the techniques or one of the approaches for finding these maxes and mins is, if you have a graph that is smooth, like this one, is to look for those horizontal tangent lines. Right? But sometimes you might have something that looks like this. Right? Now, this is a really sharp valley, and this down here is still a minimum of some sort. It might be a global minimum, it might be a relative minimum. I'm not sure because I don't know what's going to happen on those edges of those graphs, but I can tell you for certain around it on a small interval containing 0, that's the smallest point, the lowest point, and if it's the lowest point, then it's going to be a relative minimum at the very least. Right? But the problem is that is not going to have a horizontal tangent line there because the behavior of the graph is weird. It has a point that is not differentiable there. If you want to get fancy about it, there's a mathematical term for it. It's called a cusp. Right? It's this immediate change in the value of the derivative where it's undefined at the point, and left and right of it, it looks like we're approaching infinity on both sides. Vertical tangent lines almost. Right? All right. So let's look at our mathematical definition, because my job is to be able to find these things. I need to be able to find them, whether they are nice, pretty ones that look like these two, or whether they're kind of uglier and look like this one. Now, if you took this graph right here and flipped it upside down, you could make the exact same argument for a high point, a maximum. If you had some sort of graph that did something like this, then that would be a maximum up there. Okay. So my job is able to find these things. So I need to know how to find them. So let's take a look at some definitions, and then we'll take a look at the approach to identify and find these things. So here is our definition of relative extrema. All right, so let's take a look at our definition that we're working with. It reads, if there is an open interval, and I'm just going to stop right there. Remember, open intervals don't contain endpoints. So if there is an open interval containing a value c on which f of c is a maximum, then f of c is called a relative maximum of f, or you can say that f has a relative maximum at the point c comma f of c. Okay. Number 2 just takes that and flips it upside down and says if there is an open interval containing c on which f of c is a minimum, then the f of c is called a relative minimum. So basically what we're saying here is when we look for maxes and mins, we define everything to begin with as a relative max or a relative min, and then if we can take that extra step and say, hey, look, this minimum happens to be the smallest of all the minimums for its entire function, then we can relabel it as a global min or a global max. Right? But everything starts out as a relative min and only can ever take on the definition of absolute if one of two things is true. One, if you are on a closed interval and you can show it's the highest point on that closed interval, or 2, if you are on an open interval, that is the entire domain of the function, like say negative, negative, positive, if you can show that it is the highest maximum of all of the maximums that exist. All right, so here's our first example. My problem, or my job, is to identify any local extrema and then to classify and see if any of those can be renamed as absolute extrema. So I'm going to go ahead and use my blue highlighter and highlight high points that I see. So this is a high point, this is a high point, and this is a high point. Now I'm going to use my yellow highlighter and highlight low points. This is a low point, and this is a low point. Okay? So the fact that I have high points and low points means that I can talk about extrema. Okay? So the first thing I'm going to do is I'm going to talk about my maximums. Okay? So what are we looking at in terms of maximums? Well, there is a maximum at the point negative 137. There is a maximum at the point, what does that say, 1,5? And there is a maximum at the point 432. These are all some sort of maximums because for some interval, they are maxes. Right? Okay. Well, I'm pretty sure that I can just simply say that this one is just a relative because it's not a highest point and it's not the highest point. Right? And now I'm looking at the y values, I'm thinking I can say that this one is a global or an absolute. And so then what about this one? Well, here's the weird thing about endpoints. Endpoints are either absolutes or we don't care about them. I cannot call that one a relative because it doesn't fit the definition of a relative. All right. So I'm going to go back up here. The definition of a relative maximum required that there is an open interval containing C. An open interval containing C means something like this on a number line. It means here's C. An open interval containing C is a little bit to the left and a little bit to the right. And that interval right there. This endpoint, I can't go to the right of it. I can only go to the left of it because the graph stops there, because the interval is closed and stops at 4. I can't go beyond 4. So then that endpoint ends up actually being a whole lot of nothing, because I can't even call it a local maximum or a relative maximum because I can't make it fit the definition. I need that interval around it. Okay? I can call this one over here an absolute or a global maximum because the global definition does not require the interval around it. It just requires that that is the point on the graph on some interval, in this case the interval negative 1 to positive 4 inclusive, where it is the highest y value. Right? All right. So now what about minimums? We've got two of them. We've got a minimum at the point 0, 0, and we have a minimum at the point 3, negative 27. Right? Well, I can call them both locals or relatives because I can do the whole interval around on both of them. Right? But this one is also smaller, lower in y value, negative 27, than the other one. So while the best I can do with this one is to call it a relative min or a local min, while I can take this one and go one step further and say this is going to be a global minimum. You would not be incorrect if you called this a local minimum, because it is, or a relative minimum. It fits the definition. But we can also take that thing one step further and say, while yes, it is a local, it is the smallest of all the locals. Therefore, it is the global minimum. All right, so takeaway from this. Endpoints can't be relatives. Endpoints can only be absolutes. Points in the interval can be either relatives or absolutes, but endpoints can only be absolutes. Okay. Find the value of the derivative at each of these extrema. Okay. Now, earlier we talked about how the derivative is going to be related to finding these. So what I would like to do is I would like to take a look at these functions and find the value of the derivative and see what's going on there. Okay. So this first one over here on the left is that horrible function 9 times the quantity x squared minus 3 over x cubed. I'm just going to copy it down here. Okay. And I'm going to pull the 9 out. The reason I'm going to do that, that's right. The reason I'm going to do that is the 9 is a coefficient, and so when I take the derivative, it's just going to drag along. It'll just be a coefficient of the derivative, so I just want to kind of hold it off to the side so I don't have to worry about it. Now, it does not appear. I could solve this one. I could take this derivative. When I take my derivative, when I dx this thing, when I use that operator to take the derivative, I could use the quotient rule. But given that this denominator is a monomial, and I'm lazy and I don't want to use the quotient rule, I'm going to rewrite this thing before I take the derivative. And I'm going to say that f of x is equal to 9 times 1 over x minus 3 over x cubed, or 9 times x to the negative 1 minus 3x to the negative 3. Do you see why I did that? Big picture, that's going to be easier to take the derivative of. So now when I take the derivative, I get that my f prime of x is going to be equal to 9 times negative x to the negative 2 plus 9x to the negative 4. So there's my derivative, but the problem wants me to find the value of the derivative at this extrema. So that extrema is when x is 3 and y is 2. So I'm going to evaluate my derivative, that is, I'm going to find f prime of 3. So that's going to be 9 times the quantity negative 3 raised to the negative 2 plus 9 times positive 3. I don't know where that negative came from in my term there, to the negative 4. So I have 9 times, negative 1/9, right? Plus 9 over 3 to the 4th is what, 81? But 9/81 reduces down to, that's 1/9. And so then in here, I have negative 1/9 and positive 1, I have 0. 9 times 0 is 0. So the value of the derivative there is 0. The value of the derivative, this maximum, is 0, which means that there's a horizontal tangent line there. And if there's a horizontal tangent line there, maxes occur. Looks like a maximum here is going to occur when the derivative has a value of 0, when there's a horizontal tangent line, when the instantaneous rate of change is equal to 0, when the slope of the curve is equal to 0. All of those phrases mean the same thing. Here's a minimum. My job is to take the derivative and see what is the value of the derivative at that relative minimum at the point 0, 0. All right, so what is the derivative of, sorry, I wrote too quickly. I'm jumping ahead of myself here. What is the derivative with respect to the independent variable x of the function f of x, which is the absolute value of x? Well, it's tricky because I can't take the derivative of this. I don't have a rule for that. So what I'm going to have to do is I'm going to have to rewrite it as to what it is. The absolute value function, I'm sure you've seen this somewhere before, at least I hope you have, is really a piecewise defined function. Okay? Where for input values greater than or equal to 0, it does nothing. And for input values less than 0, it changes the sign. Right? So we need to take the derivative of that piecewise defined function. And so when I take the derivative, I get that f prime of x is equal to 1 or negative 1 for x is greater than or equal to 0, or for x is less than 0. But there's a problem. This equal to can't be there. And I know this is a hard one to wrap our brains around, and it took me a long time when I first learned calculus to make this one work too, because the equals to is here, so why does it disappear here? Well, the reason being is derivatives are technically limits, right? Do you remember this definition from a little bit ago? And so if I'm trying to take the derivative at 0, right, this right here is going to require that I'm allowed to approach 0 from both sides. And because of the way absolute values are, whether I'm left of 0 or right of 0, that left-hand limit and that right-hand limit aren't going to be the same value. That left-hand limit is going to have slopes of negative 1. That right-hand limit is going to have slopes of positive 1. So this limit right here isn't actually going to exist. And if that limit doesn't exist, what does that mean about the value of the derivative there? Well, if the limit doesn't exist, the value of the derivative doesn't exist. And so weird corner on a graph is a minimum. That's true. But this function is not defined there in terms of a derivative. The derivative of this function is not defined there. So this is not an example where a maximum or a minimum would be a horizontal tangent line. It's an example of a maximum or a minimum where the value of the derivative does not exist. Right? All right. Using that logic, what would you expect to see here for this maximum and this minimum in terms of the value of the derivative? Well, this graph looks more like this graph, a smooth curve that kind of goes up and then down, or down and then up. So I'm expecting not to have this problem where the derivative won't exist. I'm expecting to see two horizontal tangent lines here where our slopes would be 0, where our derivative would be 0 at those 2 points. So I'm going to go ahead and do the math and see if that is true. Okay? So the first thing I need to do is to take the derivative with respect to x of the function f of x. F of x is the function sine of x. Right? That then gives me that f prime, or the derivative here, is equal to cosine of x. And now I'm going to evaluate cosine at the max and the min. I'm going to evaluate the derivative at the max, which will be f prime of pi over 2, which is the cosine of pi over 2, which is 0, which means that yes, it does have a horizontal tangent line there. And now I'll evaluate the derivative at the min, which means I'll find f prime of 3 pi over 2. 3 pi over 2, that means the cosine of 3 pi over 2, which again is 0, which does mean we have another horizontal tangent line there. So what are we supposed to take away from this? Well, our job is going to be to find maxes and mins. And so how are we going to find them? We can't just keep looking at graphs every single time because we're not going to know all the graphs every single time. So we need to do something else. We need to use calculus. So I hope you're seeing where this is headed. The maxes and the mins are going to occur when the derivative is 0 or when the derivative doesn't exist, which means it's going to become our job, it's going to become incumbent upon us to be able to find where the derivative is equal to 0 or where the derivative does not exist. Okay? That'll be part 3. I'll see you all back here for part 3.